So today in this video, we're going to talk about quantum Hamiltonian simulation. So let's first talk about what is a Hamiltonian. So in quantum mechanics, the Hamiltonian is the observable corresponding to the energy of the system. So it's typically denoted by this letter H, and it is a Hermitian matrix. So H is equal to H dagger. And as I said, it is the observable that corresponds to measuring the energy of the system. It often appears in the Schrodinger equation. The Schrodinger equation is written like this. So IH L by del T psi of T is equal to H psi of T. So this Schrodinger equation represents the evolution of a quantum state. And this operator is the Hamiltonian operator. So this is Hamiltonian. And this is the quantum state. And the solution to the Schrodinger equation is given by psi of t is equal to e to the minus I h psi 0, where psi 0 is the initial quantum state, and this is t. And this is h bar, right? So this is actually in finite dimensional systems, this will be like exponentiating a matrix. So where the matrix exponential e to the a is defined as identity plus a square over 2 factorial and so on. So this is the solution to the Schrodinger equation when h is time independent, when the Hamiltonian h is time independent. So one can describe the quantum system, such as a spin system or any other quantum system, in terms of its Hamiltonian. And the dynamics of the system is governed by this operator, which is a unitary operator. So this is the unitary operator that determines the dynamics of the systems. So for example, in quantum chemistry, you could be given an Hamiltonian, and then you want to see what the dynamics are, and maybe you want to know the ground state of the system or the ground state energy of the system. So in quantum chemistry, for example, quantum chemistry, you may be given a Hamiltonian that let's say looks like this. So this is summation ij, and this is an example of a one-dimensional system, some real constant jij and zi zj. So these are the poly z operators. So zi means the poly z operator acting on the ith sort of point of the chain and tensored with the identity res over the other sites. And zj is the poly z operator acting on the jth site, and maybe I and j could be nearest neighbors or something like that. So some Hamiltonian such as this may be given. So this I xi, and then you want to sort of know how this quantum system evolves, and therefore you have to exponentiate this system and construct a unitary, but you want to construct the unitary such that the unitary can be built in a as a quantum circuit. So you want to decompose this this unitary that governs the dynamics of this quantum system as a single qubit and two qubit gates. So typically H will be given as a sum of local Hamiltonians. So this will be H1, H2, Hm. And maybe each of these HIs are acting only on two qubits. So each HI act only on neighboring qubits, right? The question is, can we build a circuit for this, for the dynamics of the system, and can we build an efficient circuit for the dynamics? So the question is, can we efficiently simulate this Hamiltonian? And what does it mean to efficiently simulate? Well, it means that when we construct this unitary U, which is maybe, let me call this U tilde, will be an approximation to e to the minus I h bar h1 plus h2 plus hm t. We want to construct an approximation. Then the number of gates that we use. So U tilde has order of polynomial in n t and 1 over epsilon. So number of gates are polynomial in these three quantities, where n is the number of qubits that you are using, t is the time of evolution, and epsilon is the sort of approximation. So u minus u tilde norm of that may be less than some epsilon, right? And so how do you efficiently simulate this? And that is where we use this. So one of the ways, there are many ways, but one of the sort of standard ways of doing it is through this Lie-Suzuki-Trotter formula. So you may know that if I try to exponentiate a matrix, so if I take e to the a plus b, in general, this is not equal to e to the a times e to the b. If this was the case, then this would be easy to sort of construct. But the Lie-Trotter formula says that this is not true. However, e to the a plus b is equal to e to the a times e to the b plus some error, which is of order of norm of a times norm of b. So this is the first order approximation to the Lie-Trotter formula, right? So the idea is to sort of exponentiate this, and I'm going to ignore the h bar and minus term. So basically the idea is to calculate this unitary or simulate this unitary effectively, where let's assume for the time being that this is h is equal to the sum of just two terms which are local. So they act only on two qubits. So h1 plus h2. Right. So how do we simulate this? Well, we can write e to the I h t as e to the I h t over r raised to r, where r is to be determined. Okay, so we have sort of divided these evolution into small little time steps. And then since h is equal to h1 plus h2, so this is e to the I h1 plus h2 t over r raised to r. which is by the Trotter formula over here. So this is the Lie-Trotter formula. This is equal to e to the I h1 t over r times e to the I h2 t over r plus some error term, we call that e raised to r. And the error term in this case, so the error term is equal to norm of h1 t over r times norm of h2 t over r. So this is, in fact, the error term is of order t square over r square. Right? Now, well, if you look at this, there are two evolutions over here, these two, and they have to do these r times, right? So if I take my u tilde to be equal to, which is an approximation to be e to the I h1 t over r times e to the I h2 t over r, then the question is how large must r be so that I can reduce this error term over here, right? And so in general, what is true is that u minus u tilde, right, the norm is less than due to this. So it's a product of um, r unitaries, and each of them introduces this error e. So this is actually less than, one can show that this is less than r times e. And this is of order, due to this, is order t square over r. But we want to make this less than epsilon. So how large should r be? So we need to need u minus u tilde to be less than some epsilon, right? So r, from this you get r should be equal to order of t square over epsilon, right? So we have to, if I take u tilde to be this, then if I take r to be order t square over epsilon, then we should be able to get this approximation u tilde to our evolution u to be less than epsilon. And then how many gates do I need? Well, the number of gates are, well, if you look at this, there are two gates, two qubit gates inside here. And there are, you have to apply them r times. So there are, in fact, two r gates, right? So number of gates, two qubit gates are equal to 2 times r, which is also of order t square over epsilon, which is polynomial in t and 1 over epsilon. Right now, one can extend this to a Hamiltonian, which instead of, so extend this idea, so extend this to H being, instead of just two local Hamiltonians, it could consist of m local Hamiltonians. So this is something like this, where each of these Hamiltonians are acting on two qubits. And then I could make my u as e to the I h1, just like before, t over r, e to the I h2 t over r, e to the I hm t over r plus e, the error term, raised to r by the Lie-Trotter formula. And in this case, our error term norm of this will be of order. One can show that this error term can be, this has to be shown, but this one can show that this is of order m square t square over r. And so if I want u tilde, which is e to the I h1t over r, h2t over r, I hm over r, such that u minus u tilde less than epsilon, then one can do the same calculation and show that r has to be of order m square t square over epsilon. Right? This is because of the fact that u minus u tilde again is less than r times error, and error is over here, right? So we need to have these many times that we have to evolve this local unitaries. And then how many gates we do need? The gates are, well, if you look at the number of gates, these are m gates, and each of them have to be applied r times. So number of gates is equal to m times r is equal to order of m cube t square over epsilon. Right. So this is one technique to sort of simulate a quantum Hamiltonian. And why do we need to simulate these Hamiltonians? Because often quantum systems such as quantum chemistry, in quantum chemistry, they're described by Hamiltonians, and we want to be able to see the dynamics or evolve the dynamics of the system. And the way to do it is to write down the Hamiltonian and then write the unitary as e to the I h t, where t is the time that you want to simulate the Hamiltonian form, and then use the Lie-Trotter product formula to sort of write the Hamiltonian as sum of local Hamiltonians, and then use the Lie-Trotter to write them as local gates acting on at most 2 qubits. There are other techniques to do this